I was in a car accident, had my seatbelt on, didn't do much. I hit my head off the dash. Head trauma is what I'm looking at. Gonna need surgery, probably a craniectomy. So now I've got to see which implant is right for me. I went on the internet and found Cranial Connection. I found a doctor to find out my direction. 3D printing my part online, getting peak on my skull now. Cranial Connection, match me with the right implant for free. Get connected for free with Cranial Connection. Get connected for free with Cranial Connection.
Hello everyone, and welcome to Cranial Connections. Today we are going to be talking about intracranial pressure. Patients that have intracranial pressure could be caused by trauma, tumors, a hemorrhage, emphyema, or just some type of pressure in which they're going to need their cranial vault removed in a surgical procedure called a decompressive craniectomy. These reconstructive surgeries are often difficult even for some of the best surgeons around because of the sensitivity involved in the systems and the uniqueness of each defect. Once the patient is neurologically stable, the removed part of the cranial vault can be reinserted. However, there are often issues with this reinsertion, including resorption, which is seen in the figure on this slide, as well as infection issues associated with putting the same cranial vault back in the patient. Remaining defects may cause both functional and aesthetic problems, exposing the need for a synthetic implant. Each year, there are approximately 2.2 million bone graft procedures performed, and this number is only rising. The main aim of a bone substitute is to restore the biomechanical properties of the patient's defective bone, as it is important that the physiological functions of the replacement are closely related to the bone's unique properties. In principle, the most gold standard type of bone that we could use for a replacement is autogenous bone because it contains living cells, an osteoconductive scaffold, and human growth factors. Allografts have both osteoconductive and osteoinductive properties, but lack the osteogenic properties due to their lack of viable cells. Although these materials are theoretically available in many shapes and sizes, concerns with these materials are sterilization, tissue processing, donor site morbidity, and a deactivation process of proteins in the extracellular matrix. For this reason, polyether ether ketone has evolved to be one of the most useful biomaterials available. This is otherwise known as PEEK. It's actually a high-performance organothermoplastic polymer that was developed in the late 1970s by the U.S. aerospace industry, and its medical usage started in the late 1980s. The properties of PEEK, such as high mechanical strength, chemical and degradation resistance, and thermal stability, have contributed to its increasing use for bone implants. PEEK is useful in the body because it does not cause any harmful reactions or release any harmful constituents to human tissues, and thus it's a bioinert material. PEEK is especially useful in the medical field because it can be sterilized in an autoclave or with gamma radiation without significant changes to the material's properties. Perhaps one of the most compelling advantages of PEEK is its ability to be 3D printed. 3D printing allows the implants to be made specifically for each patient, an advantage over traditional forms of manufacturing. In order to capture the specific requirements of the implant for a patient, such as shape, size, and mechanical properties, the implant area is scanned with MRI or CT imaging, and the patient data file is converted to a 3D file that can be used with additive manufacturing technologies such as 3D printing. PEEK is also an effective alternative to metal implants because metals actually become absorbed by the surrounding tissues and cause streaked artifacts in CAT scan images, whereas the metals themselves are incompatible with MRI technologies. This makes post-operative analysis of the patient's well-being somewhat difficult. The most common 3D printing techniques for implants are selective layer sintering, SLS, and fused deposition modeling, FDM. However, SLS struggles with high cost and material management, whereas the printing conditions for FDM can be difficult due to high fusion temperature of PEEK. High temperature laser sintering is then actually used as a modified form of SLS, and it's able to print high temperature polymers. A schematic of this system is shown on the left-hand side of the screen. As mentioned before, there are many advantages to PEEK, and I'd like to go a little bit more into detail about some of these. PEEK is bioinert because of its chemical and degradation resistance within the body. It also has a high thermal stability, which means it's very unlikely to react at the human body temperature. PEEK also has a low moisture absorption and high flexibility, with a low elastic modulus of about 3.5. PEEK is also lightweight, so it enhances the comfort, safety, and quality of life for the patient, and it is strong enough to hold the load of a human body without permanent deformation, but it is also flexible. Now I would like to dive a little bit into some of the real science studies that were done with cranial implants. The Beretta group was able to build 13 different cranial implants with build orientations of horizontal, vertical, oblique, and inverted horizontal as shown on the left, for the exact location shown on the right. Dimensional accuracy results suggest that for the interior surface of the implant, the horizontal and oblique building orientations were most accurate, whereas for the external implant, the horizontal and inverted horizontal building orientations were the most accurate. Additionally, the inverted horizontal and horizontal implants weighed about 25 grams, which was a slight advantage over the oblique and vertical building orientations. In terms of mechanical testing, it can be seen that the inverted horizontal had both the highest first failure load, making it the most ideal building orientation. Right now, we are offering a special where this surgery costs only $8,500 with a 100% money-back guarantee. But you're going to have to act fast if you'd like to get this deal. There is a limitation disclaimer. 3D printing requires a highly educated and highly skilled human part designer. You also must have specific computer software in order to build these designs. One implant is suitable only for one patient. Both the materials and 3D printing equipment are very high cost. Previously, skull implants have been made with different metals such as stainless steel, gold, titanium, and cobalt chromium. These have favorable strength and excellent friction resistance. However, their high strength modulus does not match that of the human body. This causes issues such as prosthetic loosening. The other issue, as mentioned earlier, is that metals can absorb into surrounding tissues and cause streaks in the patient scanning technology. One specific study looks at the titanium reinforced calcium phosphate bone implants. These materials are brittle, but also biocompatible, osteointegrative, and osteoconductive. Only 5.7% of patients with this type of implant have developed complications. Although this sounds like a lot, other bone implants have a failure rate as high as 64%. This material also has a first fracture load similar to that of PEEK with 463 newtons and a maximum load of 808 newtons. However, with improvements for PEEK on the way, such as additional strength and antibiotic reservoirs, PEEK is the way of the future. Thank you.